Way back in Chapter 2, a lifetime ago, we talked about how the molar mass of a compound is just the sum of the atomic weights of each atom in grams per mole. Your textbook covers it again in this chapter just to remind us. You can also do the same thing with ionic compounds. The only difference is we call it the formula mass instead of the molecular weight, but they're essentially the same thing. We typically don't actually measure individual atoms though. So how do we get this chemical formula? We have to find what we can actually measure, which is relative mass of elements. While it might make sense to express this as a fraction, and it would translate more directly to chemical formulas, it's a lot easier to find this as a percent, since it's molar ratios, not mass ratios, that will give us the clean fractions. We get these, again, as percent compositions. But we can still get to the mole fractions if we know the atomic masses. Start off by making sure that we have collectively defined percent in the same way. Percent literally means per hundred, cent being the Latin prefix for hundred. So when we say that something is, say, 10% carbon by mass, what we are really saying is that 10 parts in every 100, or 10 parts per 100, is carbon by mass. Even if we don't actually have 100 grams of something, the percent can be interpreted that way. So say we have an experimental set of data that tells us we have a compound that is 87.5% nitrogen and 12.5% hydrogen. We can choose whatever mass we want and the ratio will still be the same. I find it easiest to arbitrarily say that I'm working with 100 grams of this substance, which means that 87.5 of those 100 grams are nitrogen and 12.5 grams are hydrogen. The value here is that we've used an arbitrarily total amount to express that ratio, and that was in percents, as a ratio that's in grams. Ratios in grams still don't mean anything, but we know how to convert grams to moles already. We've done it lots. So if we start out by saying there are 87.5 grams of nitrogen for every 12.5 grams of hydrogen, we can use the molar mass of nitrogen and the molar mass of hydrogen to convert that same ratio into a mole ratio. Looking at the value of the ratio, we know that we aren't going to have 12.5 hydrogens in a molecule. This fraction can be simplified to 1 mole of nitrogen for every 2 moles of hydrogen. While this simplification is relatively easy, if there are a 3:2 ratio, it might be harder to simplify. I always take the large number and divide it by the smaller number if I can't immediately recognize the ratio. Here that gives a value of 2, indicating that there are 2 moles of the larger number of hydrogens compared to the 1 mole of nitrogen. If that ratio is 3:2, the larger number divided by the smaller number would be about 1.5, which is probably easier to recognize as equivalent to 3/2 than whatever number we would have started with. Once we have a ratio of moles in a simple fraction, that gives us the empirical formula. Here NH2, 2 H's for every N. Associated with this empirical formula is an empirical mass, the sum of all the atomic weights, which is here about 16 grams per mole. The empirical formula and the empirical mass may be true values for this molecule, but the true value might also be some multiple of these. We don't know this from the data only because we only know the relative amounts, we don't know the absolute mass. However, mass spectrometry often allows us to calculate actual masses for molecules. And if we know the actual mass, we need only to divide it by the empirical mass to find out how many times we need to repeat that empirical formula. Here, since the actual mass is 32 grams per mole, we know that there are 2 sets of NH2, each weighing 16 grams per mole in the actual formula. So the actual formula would be N2H4 instead of NH2. So we see that an understanding of percent as a ratio compared to 100 grams of total substance allows us to calculate empirical formulas, and with an actual mass value, we can find an actual formula as well. A quick end note, the numbers we used here came out perfectly. Because these numbers usually come from real data, ratios might not look exactly as whole numbers. It might look more like a 1.99 to 1 than a 2 to 1. We use common sense to tell us that it's probably a simple 2 to 1 ratio rather than a 199 to 100 ratio for this molecule. This figure from your text gives you a flowchart to describe what we just did. We have a ratio initially from percents, which we can convert to a ratio of masses if we use a common assumed amount. It doesn't matter what it is, but I find it convenient to use 100. Mass ratios can be converted to mole ratios using molar mass values for each atom, which, when simplified, gives us the empirical formula. Now that we've done one together, see if you can figure out the empirical formula for a molecule that's 20% hydrogen and 80% carbon. We begin by assuming 100 grams of the compound, so 20 grams would be hydrogen and 80 grams would be carbon. That 20 grams of hydrogen at a molar mass of 1 gram per mole is the same as 20 moles of hydrogen. 80 grams of carbon, on the other hand, each having a molar mass of 12 grams per mole, is 80 over 12, or 6 2/3, about 6.67 moles. When I take the ratio 20 over 6.67, I get about 2.99. Because that's really close to 3, I'm going to say that it's a 3-to-1 ratio of hydrogen to carbon. So the empirical formula is CH3. If you try to draw a Lewis structure for CH3, you can quickly identify that CH3 cannot have a correct Lewis structure. There are only 7 valence electrons. So this correct empirical formula is associated with a different molecular formula. Now, if we're given a molar mass for this compound of 30 grams per mole, we can find what the actual formula is. Go ahead and give it a shot. Since CH3 would have a mass of 12 plus 3 times 1, 12 for the carbon and 3 times 1 for the 3 hydrogens, that would equal 15 grams per mole. So there'd need to be 2 CH3 units at 15 grams per mole to make the 30 grams per mole that we have in the actual mass of the compound. So the actual formula would be twice the empirical formula. Instead of CH3, we'd have C2H6. We spent the last few slides talking about how we can figure out the composition of compounds and use it to find actual formula for those compounds. So we've been talking about what makes up compounds. That's one type of matter that we study in chemistry. Compositions of elements are trivial. They're just the element itself 100% all the time. So we know how to talk about composition in pure substances, either elements or compounds. Mixtures are a little bit more difficult to talk about, particularly heterogeneous mixtures. So much so that we'll usually separate out phases or digest them all into one phase so we don't have to deal with those heterogeneous mixtures. That leaves homogeneous mixtures, which are by far the most common way that we analyze matter in chemistry. Homogeneous mixture is a little cumbersome, so from here on out, we'll just call them solutions. But solutions are really a way of talking about homogeneous mixtures, different names for the same thing. There are a ton of definitions associated with solutions, so we're going to spend the next couple of minutes using Throwback Mountain Dew, my favorite fizzy lifting drink, to simultaneously give a real-life context for these definitions and, at the same time, work towards getting me a product placement agreement from PepsiCo. Fun fact in case you didn't know it, the ingredients list on a food and beverage product is listed in the order of the amount added by mass. So the first item listed, this picture of a Throwback Mountain Dew, is, in this case, carbonated water. So it's the thing present in the largest amount. Conveniently, that matches with our definition for solvent, the thing present in the largest amount in a solution. Carbonated water is our solvent, and it will dissolve everything else into that solution. Strictly speaking, carbonated water is already a solution. It's water with carbon dioxide as a solute, a component that's present in smaller amounts. To really understand what's going on with the solution, we can't just know what there is more of and what there's less of. We also need to know the concentration, the ratio of the solute, the thing being dissolved, to the solvent, the thing that's doing the dissolving. Anyone who has a carbonated beverage knows that you can have different concentrations of the same solution. A freshly opened can of pop has a higher concentration of carbon dioxide. It's more fizzy. A can of soda that has been sitting around for a while has a lower concentration of carbon dioxide. It's less fizzy. Usually we don't talk about concentration only by fizziness. We use a ratio of the solute to solvent in a number of different forms: volume per volume, mass per volume, mass per mass, or mole per volume. We'll talk more about concentration units in the next lecture. What we can talk about with just fizziness is solubility. Ever notice how a Coke gets flat faster when it's warm than when it's cold? That's because solubility, the maximum concentration of a gas, is higher in cold solvent than it is in warm solvent. So its solubility is higher when it's cold. When the soft drink finally stops fizzing, that doesn't actually mean that the carbon dioxide is gone. It just means that the carbon dioxide is saturated, that the solubility of the carbon dioxide is equal to that concentration, so you don't see it bubbling out anymore. When the tonic is unopened, it is under pressure of carbon dioxide. As soon as the can is opened, the solution is more concentrated than its solubility. It's a supersaturated solution. Any change in condition, like the release of pressure, leads to a rapid removal of solute from solution. If the fizzy is left out to warm and release carbon dioxide, it will generally decrease to its saturation point. But if you cool it down again, the solution will remain unsaturated. It's hard to get that carbon dioxide back in. And so we would have an unsaturated solution. The term concentrated solution refers to carbos that are near the solubility point of solute that is reasonably soluble. It's usually only used when solubility is high, not generally the case for gases. This drink would be pretty concentrated in sugar though. A dilute solution, on the other hand, is a solution that's far from the solubility point. Again, usually talking about something that has a reasonably high solubility point. In soda waters, the actual sodium concentration is considered dilute because sodium ions are very soluble in water, on the order of hundreds of grams per liter, while the actual sodium content will be in milligrams. So there you have it, our whirlwind tour of solution definitions and fizzy lifting drink synonyms. While we have many concentration units to choose from, the chemist's concentration of choice is molarity. While many measurements don't relate directly back to what's happening at an atomic scale, anything with mole units do. Since molarity is moles divided by liters, it can readily convert a volume to moles and moles to volume. For this reason, molarity functions for volume measurements in the same way that molecular weight functions for mass measurements. We can use molarity to convert back and forth between volume and moles. One of the most common laboratory manipulations is a dilution, where additional solvent is added to a solution. Whenever we add solvent, it cannot change the total amount of solute, the thing being dissolved, but we do make the solute less concentrated, which is also referred to as making the solution more dilute. More dilute equals less concentrated. You can see in the picture the visual difference in concentration of the copper nitrate solution, even though the total amount of it is the same. The math is pretty straightforward. If you have a solution of concentration M1 in molar units with a given volume L1 in liters, you'd get an N in moles by multiplying these. You'd always have the same moles no matter how much solvent you add. So if the volume of the solution changes by a dilution or by a concentration, that number of moles will need to stay the same. So any molar concentration times liters will equal any other molar concentration times the volume in liters for that same solution. Using molar and liters gives nice clean mole units for N, but in actuality we never need to solve for what that N is, just the new concentration or volume. And for that reason, it doesn't matter at all what units we use for concentration or volume in these types of problems, as long as they're the same on both sides. So if we have milligrams per deciliter as the concentration and tablespoons as the volume, it won't make half an ounce of difference as long as the new concentration is also in milligrams per deciliter and the new volume is also in tablespoons.